Okay, so now that we learned how entropy relates with microstate, we can start to put everything back to the application that we're interested in, which is predicting the direction of a chemical reaction to see if it's going to be spontaneous or not, right? But before we can do that, there's one more thing that we need to do, which is just figuring out what is the change in entropy qualitatively. So right now we're just doing it based on the behavior of the systems from reactants to products. Later on, we're going to actually calculate it. Right now, we're just going to see if the change in entropy is going to be positive, which means that that process is going to be spontaneous, versus a change in entropy where it's going to be negative, which means that it's not going to be spontaneous. So again, the idea that I want to remind you is that the second law of thermodynamics tells us that for any process to be spontaneous, we want our delta S of the universe to be positive. Okay, all right. So let's take a look at some of the changes that we typically see in chemical reactions and want to see which ones is going to give us a positive entropy change. The first one is temperature change. Entropy, we have seen, is going to increase as temperature increases, right? And so the idea here being that if you have lower temperature, basically the values of the energies is going to be more restricted. There's not going to be as many energy levels that are accessible to your particles. If you have a higher temperature, there's just going to be more energy levels that are accessible to the particles, and because there's more energy levels that are accessible, there's also more ways to distribute those particles, so thereby resulting in more microstate. If there's more microstates, that means it's going to be a higher entropy. We can actually take a look at it. These are what we call absolute entropy values for some different temperature values. For copper, in this case, we can see that at 273, the entropy value is 31 joules per Kelvin, whereas at 298 is 33.2 joules per Kelvin. I'm going to explain in a later section how we get these numbers, but right now it's just to show you that as temperature increases, when we measure the entropy for a particular substance, in this case copper, we do see an increase in entropy. The other properties that are related to entropy changes are physical states as well as phase changes. Okay, so if you look here, we talked about this before also, that as you go into the more free state, which is the less ordered state, like the gas state, there's going to be higher entropy, whereas when you're in the more organized state, more ordered state, which is the solid state, you're going to have a lower entropy. We can actually see this with several examples. Here's sodium. In the solid state, the entropy value is 51.4 joules per Kelvin, whereas in the gas state, the absolute entropy value is 153.6. And again, I haven't told you how we get these numbers yet. We'll talk about it later, but that's just a comparison of solid and gas. Water in the liquid state has a 69.9 joules per Kelvin entropy value, whereas in the gas state, it almost triple that number, okay? Whereas the graphite, which is carbon, 5.7 in the solid state, in the gas state, look at this, 30 times larger than that solid state entropy. Okay. In fact, some of the reasons why this is happening is because in the solid state, actually, of those three kinetic mode of motion that I told you about, which is the translation, the rotation, and the vibration, only two of them are allowed with solid, because solid can't really translate. So solid particles are really packed tightly like this. So all they do is they can rotate, they can move around their center of mass, they can vibrate next to the other molecule, but they can't really, this particle can't really jump to this side, which is translation. So translation is automatically not allowed for solid. For liquids and gas, they're allowed, right? So there's a little bit more modes of motions, which means more energy levels accessible to substances that are in the solid and liquid state. They're in the liquid and gas states compared to the solid state. And in fact, that's what we see. We see that as we heat a substance up, starting from 0 Kelvin all the way to, room temperature, which is about 298 Kelvin, we see that the value of entropy also goes up. And again, this is an experiment that I'll describe to you when we get to the third law of thermodynamics. Another process that increases entropy is the dissolving of a solid or liquid in water. So we typically see that when either one of these dissolve, we see an increase in entropy. So the entropy of the solution, which is the mixture of the solvent solute, is going to be larger than the sum of the two ends separate. Okay. However, there are some exceptions, or at least some points to consider when you're looking at the entropy of solution compared to the entropy of the solute in a solvent. So some ionic solutes actually have smaller entropy in the solution state versus in the solute and solvent. So examples of these are salts that contain aluminum, salts that contain sulfate, As it happens, the ordering of the water molecule around these solutes is such that they actually make them even more ordered solution state compared to when they're separated. There's not that many of these guys, but they are exceptions to the rule. For covalent solutes, you'll see some change as well when you take, for example, alcohol, which is a covalent substance, and you mix it with water. You'll see that the entropy will increase. However, the change is not as big compared to when you have ionic substance. The reason is because with ionic substance, you're completely separating the ion, whereas with covalent solute, the separation is not as dramatic as happens in the ionic substance, okay? So here are some examples, actual numbers that we can look at. Sodium chloride is an ionic substance. This is the entropy in the solid state. This is the entropy in the solution state, okay? So you can see that there's an increase there. Now, this was one of the exceptions I just mentioned. With aluminum chloride, which is one of the salts that when it's dissolved, it actually forces the water to form a really ordered structure around it. So the entropy actually decreases in the solution state versus the solute and solvent state. Here's a covalent compound, methanol. The entropy of the liquid state is 127, whereas the entropy in the solution state is 132. So there is an increase, but it's just a tiny increase when you compare it to that increase that we observe in the ionic substance. Now, what about if you dissolve a gas in water? Because notice that in this number 3 here, I'm mentioning only solid and liquid. A gas actually does exactly the opposite. The reason is because a gas is already the highest entropy state. So if you were to take a gas and you put it in water, the gas now has to be surrounded by a bunch of water particles, right? So it makes that state actually more ordered than when the gas is by itself, just floating around, those individual gas particles. So as a result, when you look at gases in its free state, for example, for oxygen here, it has an entropy of 250, but when you mix it with water, it actually has an entropy of 110. So the entropy has decreased. So in other words, that process of dissolving a gas is not going to be spontaneous, okay? Because the entropy change is negative. The last point I want to talk about is atomic size and molecular complexity. So this is just kind of comparing how big particles are and how complex they are. Complexity here refers to things like branching, how many branches that particular structure has, okay? And this is the last thing you want to look at. So you really want to look at all these other things first before you look at atomic size and molecular complexity. If you're in the same phase, so for example, let's say you're both in the gas phase or you're both in the liquid phase, okay, you can compare atomic size and molecular complexity and see patterns in entropy value. So as long as the elements is within a period or they're similar compounds down a group, then when you increase the molar mass, you get higher. And this is the same idea as when you increase number of particles, you get higher entropy. And the reason is because the more particles you have, there are more ways, right, to arrange those particles in these energy levels. If there are more ways to arrange the particles, that means you have more microstates. If you have more microstates, that means you're going to have a higher entropy, okay? So this is some examples of those. These are all group 1 species, lithium all the way to cesium. And as you can see that as the molar mass increases from left to right, we also see that the entropy value increases, okay? We see it also with molecules that are in a group, which is this one right here. This is all the halogen covalent compounds that are bonded to hydrogen. And we can see that based on the molar mass increase, we also see a pattern in increasing entropy. Molecular complexity is a little harder. Again, complexity here refers to the fact that there's usually more atoms, more bond occurring, more branching. And so in this case, we can see that the pattern here with these molecules, this is a molecule that only has 1 bond. This is a molecule that has 3 bonds. This molecule has a lot of bonds. And you can see that there's obviously an increase in entropy value here, okay? Same thing in this pattern right here. You can see that they're all made up of nitrogen and oxygen, but the number of bonds increase as you go from left to right. And similarly, the value of entropy also increases. Okay, so I want to kind of wrap up this section. This is, again, just a qualitative measure of entropy. We're just trying to get a sense of when is entropy high and when is entropy low. All right, so let's take a look at an example and figure out which substance has a higher entropy. So if we look at 1 mole of KNO3 aqueous versus 1 mole of KNO3 solid, we're going to say that this aqueous substance here is going to have higher entropy, right? And again, the reason is because when you're in the solution state, the ions are separated. So they're more free to move, they're less ordered, and as a result, they have higher entropy. PCl3 versus PCl5, which one is going to have higher entropy? They're both gases, so state of matter is not going to be important. However, PCl5 has more bonds, right, compared to PCl3. So as a result, that one is expected to have a higher entropy. What about BaCl2 and CaF? These are both ionic compounds. They're both solids, so state of matter and the ionic or covalent type is not going to change. But you can see that barium chloride has a higher molar mass overall compared to CaF. So we'll expect barium chloride to have higher entropy, okay? And lastly, we have Br2 solid and Br2 gas. That one should be pretty easy to look at. The gas would have a higher entropy, again, because it's a gas. It's the least ordered state of all of the states of matter.